systems that we currently have, and then I'll go through previous literature to see if there is any remaining challenges and issues that we can address, and then I'm going to present our solution to those challenges as well as our results. And finally, I will conclude the presentation. So the building sector is responsible for over 1/3 of final energy consumption worldwide, other than refrigeration, water heating, lighting, and other systems. The heating, ventilation, and air conditioning system, or HVAC systems, account for the largest category of energy end use in commercial and residential sectors. They are complex mechanical systems that are also responsible for the thermal comfort of occupants, and there is always a trade-off between their energy consumption and the thermal comfort that they provide. Moreover, faulty operation of this system leads to emitting greenhouse gases, disturbing occupant and thermal comfort, and also wasting energy. So this makes HVAC systems a source for untapped and preventable energy losses that can be tackled by embedding intelligence and smart operations. As such, we see a proliferation of intelligent HVAC systems that can utilize dynamic modeling of building characteristics, replace rule-based models with adaptive control techniques, and also integrate advanced fault detection and diagnosis, or FDD, using data-driven approaches. So the goal of FDD is to minimize risk and improve operations through monitoring, fault detection, and diagnostic. And don't worry if your process and system doesn't incorporate all the steps that you can see in this picture. Actually, FDD is a tool used in the digital transformation and not an all or none concept. It's you can be somewhere between these steps. So to implement FDD, monitoring must occur first. So like if a tree falls in the forest and no one is around to hear it, it does not make sound, right? So if there is a fault and no one is monitoring that piece of equipment, does it create an issue now or in the future? Of course. And monitoring is a prerequisite for FDD, and the quality and type of monitoring will either make your job easier or harder. So data quality is important, as you must be able to trust that it's a true representation. You don't want to find yourself in a situation when your data says that a tree is still standing, but when you look at the tree, it's on the ground. So in addition, we can use technology to improve your monitoring capability. Technologies like data warehouses and also predictive analysis. And the next step in FDD is fault detection and identification. So what is the fault and where did it occur? In FDD, fault expand to a broader definition to include critical deviations. Fault detection and diagnostic software has enabled industry to detect and identify previously unnoticed deviations that are precursors to large issues. By using machine learning, our organizations can leverage computational power and always-on monitoring to pinpoint any deviation. Though simple in theory, fault detection and identification has the potential to be difficult due to system complexity. For example, root cause analysis, or RCA, can be time intensive. For this reason, many organizations save RCA for major issues and use a simplified versions for minor issues. Another potential obstacle is lagging indicators that may misdirect attention from the true issues. Once you've detected and identified a fault, what steps should you take to remedy the issue? The immediate goal is to take corrective action to rectify the fault. But an important follow-up step that is sometimes forgotten is analysis and evaluation. Once you fix the problem, how do you make sure it doesn't happen again? So there are loads of challenges here. To be more specific about those challenges, I have presented some of those here. So these are separated into technical and operational challenges. So like for example, some faults may be due to random malfunctions. Other times there may be an issue with process or operation. Regardless, you have to take time to understand if and how you can minimize the probability of the fault occurring again. So for example, do you need to make an adjustment to the logic or not? Or do you need to make an adjustment to the maintenance schedule? At a minimum, you have to keep records of what happened and what steps were taken. All layers of the organization or the building management system will appreciate a well-managed organizational knowledge in the future. The second challenge is that automation does not magically happen. This doesn't mean that the process should be complicated or require significant work on your side, but if it sounds too good to be true, it is probably is. So understand clearly what steps you will need to take to implement automated FDD, as well as the steps needed to maintain your automated FDD. Like anything, automated FDD may need tune-ups from time to time, and your software should provide suggestion on what upkeep is required. And don't worry, it shouldn't require the full-time staff. And if you're working in a commercial site, different vendors use different approaches to fault detection testing. So approaches used include regression neural networks, fault signatures, and rule-based procedures. When selecting your tool, you don't need to know the ins and outs of how the technology works, but you should be familiar enough that you can determine whether it will be a good fit for your organization or not. So for example, a tool that uses only fault signatures is going to take longer to implement at an organization that has a relatively unique process and doesn't have a pre-existing fault database. So, and there are some technical challenges as well. So we are going to focus on those parts. Like for example, the data sets are unbalanced, meaning that the number of samples that you have for faulty operation is significantly smaller than the number of samples that you have for the normal condition. And also you have to account for the false positive, because you don't have to get stuck in some alerts and warnings to the operational team, but it's not accurate. So it's going to be very hard for the operational team to trust on a system that has a higher false positive. And also you have to deal with lots of false categories. So you have to somehow manage and predict for all those faults as well. So these are the challenges. So our goal for this study is to minimize false positive for the system that we are proposing, and also maximize accuracy at the same time. And we are going to actually account for the unbalanced data, meaning that we are going to upsample the samples that we have for the faulty condition by using some white noise and etc. that I'm going to detail in the next slides. And also, other than that, we are going to propose a moving window PCA to monitor the normal condition, so that we can be trustful when something is deviating from the normal condition. We can detect that by MWPCA, and then we are building upon that a random forest classifier that can diagnose the root causes of that fault. Okay, so I have presented a bunch of recent studies on the FDD for HVAC systems, and as you can see here, we have a bunch of variety of approaches and models, but most of them are using data-driven approaches because of their high detection accuracy and all the advantages that we know of those ML algorithms. And there are a variety of machine learning algorithms that you can use, from deep learning models to supervised, unsupervised classifications like random forest, support vector machines, and all those kind of stuff. So the point is that the choice of algorithm might not be very important, because every one of those algorithms can be tuned in a way that they represents a higher accuracy. Although most of the focus of previous literature is on increasing the accuracy. So this is the first point. The second point is that the previous studies didn't consider all those aspects of the challenges that I mentioned. Like for example, some of them may consider false positive, but they don't consider the unbalanced and normal condition monitoring and vice versa. So as you can see, there isn't any study that account for those three specific challenges that I mentioned here. So we are trying to solve those problems and address those challenges in the framework that we are proposing. Okay, so here is our solutions to the challenges that I mentioned. So to minimize false positive, we are going to define a model for tracking the normal condition based on historical data. We're going to use a moving window PCA for that. The MWPCA can detect any deviation from the normal conditions. Using MWPCA leads to gaining more reliability for the models that you are producing for the forecasting stuff, because you will be sure that something is happening, and then you will try to classify that. So the PCA cannot forecast the classes of faults. It cannot root cause that. It just tells you something is happening, but you can't track that into details. We are also going to use the time series anomaly detection to validate the stuff that we are getting from the PCA, so that we have even more reliability of detection of any normal condition. The second challenge is to maximize the accuracy. So to do so, we're going to do a comprehensive hyperparameter optimization for the random forest and all the machine learning stuff that we are using, and also by minimizing the false positive, you are somehow maximizing accuracy as well. The third one is to account for unbalanced data. So we are going to classify faults according to the density and intensity. So that means that if a damper is getting a stack by 60% or by 100%, you are going to consider those classes of faults as one class. By doing so, you can artificially provide more samples for the training algorithms. Also, we are going to sample up the faulty condition using a white noise. So this is a very well-established approach that is very easy to use and very useful at the same time. Okay, I'm running out of time, so I'll try to be as quick as possible. Here is a bunch of details about the data that we have for this study. We got this from an open source database from FlexLab. This is a lab supported by Department of Energy, DOE, and these people are great people working in California, Berkeley. So yeah, this data is for a multi-zone HVAC system and also single zone HVAC systems. And the data that we consider for this study is measuring more than 270,000 measurements, and the resolution is 5 minutes. And here on the right side, you can see the distribution of the faults by their frequency. So we have the damper stack, heating coil, leaking, cooling coil stack, and temperature bias, basically. Here is our proposed framework. So apart from data acquisition, which was outsourced in this study by FlexLab, we have data pre-processing. So we have to clean the data, standardize it, and also do the upsampling. Then we'll define the normal behavior and detect any deviation by MWPCA and also time series anomaly detection. And then we are going to build a classifier upon that by using a random forest predictor. Also, we are going to measure the performance of the network by using precision, recall, accuracy, F1 score, cross entropy, and confusion matrix. Here is our results for MWPCA that we built for the normal condition monitoring. So we have 12 features, and as a consequence, we will have 12 principal components in our covariance matrix. Each of those principal components will represent and explain variance of the datasets. The point here is that you won't have to use all of those components for your model. Basically, that's the whole idea about PCA. It will do a reduction in your model. So if you have 12 features, you can see here in our case, one principal component can represent more than 95% of data variance. So as such, I'm going to only use PC1, and when I tried that based on different assets, you can see here on the right side that, for example, asset 1, which is an air handling unit, is behaving normally. And also, when you compare it to asset 2 and 3, which are also behaving normally, you can see that they have similar values. But when you consider asset 6, which has a faulty condition, then you can see that here I can detect fluctuation. So you can see that for asset 6, something is happening that is not normal. So evaluating classifiers can be done in multiple ways as there are many performance measures. A good idea is to count the number of times that instances of, for example, class C1 are misclassified as class C2. By doing this for all classes, a matrix can be created that represents the accuracy of positive and negative predictions. This matrix is usually known as the confusion matrix. Each column of the confusion matrix demonstrates a predicted class, and each row shows an actual class. The confusion matrix contains many numbers, and a more convenient option is to create an image representation of that matrix. So here we have 7 classes based on the normal and faulty state of the operation for both single zone and multi-zone HVAC systems. And also on the right side, you have a representation of true positive rate to false positive rate for the random forest, as well as 3 other algorithms that we compared with. So you can see here that a deep learning algorithm has a slightly more advantage over the random forest, but we use random forest because it's much simpler. It has a much simpler configuration than a deep learning model. And the computational time is also very good comparing to the deep learning. So you can simply use it in real-time applications, while deep learning has lots of and loads of challenges. So you can see here that random forest is operating very well. So to conclude this presentation, I would like to pinpoint some of the things that we learned from this study. The first point is that normal condition monitoring is as important as building a prediction model for fault classification prediction. So it's really, really important to say that something is not working and then to try to define the root causes of that. So this is my first suggestion to all those you guys. The second thing is that you can try to build an architecture that can use leverage overlapping models for validation of different things that you have in your system. Like for example, using time series anomaly detection to validate the MWPCA results. And also the third point is that you have to somehow account for the unbalancing of data. So it's really important to upsample if your faults are limited, which is usually the case. And the last point is that data pre-processing is also very important. Like for example, when you are conducting the MWPCA, you have to transpose data and feed it to the algorithm. And by doing so, because you are not recording all the things in different parts of the system in all those timestamps, then you will get some null values, and you have to somehow account for that. If you don't, then your model is not going to work very well. So these are my top 4 conclusions for this study. Here you can see the references that I used for this presentation. And thank you for listening.
Okay, thank you. Any questions?